Thank you, everybody, for joining me today. My name is Will Rock, and I'm an application scientist at Headwall Photonics. And in today's talk and demonstration, I'm going to start off by giving everybody a brief introduction to hyperspectral imaging. We'll go over a little bit what you saw yesterday if you attended our live demo of our drone, and give a little bit more explanation of how the sensors work, what the internal workings of the sensors are, and just basically a brief introduction to hyperspectral imaging for those that aren't intimately familiar with the technology. Then I like to break up my talk a little bit by going straight into the live demo. Over here, I have our small laboratory scanning kit, along with a SWIR 384 imaging spectrometer. And I just have some random rocks that I brought with me in my suitcase set up there. And so I'll just do a brief demonstration of how our laboratory scanning kit works, the workflow for collecting data, and I'll do a brief classification of these rocks for you all. And I strongly recommend anybody that's interested in this technology, wants to get a feel for it themselves, that after the talk, you come and see me, and if you have samples or anything that fit on a stage about that size, you're welcome to put them under there. I'll scan them. If you have a flash drive, I'll give you the data. But I hope anybody that's interested takes advantage of that because I think it's a great opportunity to try some samples that are near and dear to your hearts. And so, again, I strongly recommend that you take advantage of that. And I am here to help anybody run the system, give just a quick little training tutorial, and get your own hands dirty. I think that's always the most fun things in science, is to actually do a bit of it yourself. So without further ado, let's get on to our introduction to hyperspectral imaging. So you can see there's a repeat of the outline that I just explained to you. So intro, lab scanning kit. Then after that, I'll talk about a few examples of applications of hyperspectral imaging, mostly around the remote sensing / mining area, because I know there's a lot of geologists in the audience. However, the application space of hyperspectral imaging is very broad. And so anybody in the audience that's interested in stuff like precision agriculture or machine vision inspection, et cetera, please speak with me afterwards, and we can talk about more applications that might be more interesting to you. So this is my little cartoon of the entire electromagnetic spectrum. Most of you are probably familiar with this, and hyperspectral imaging is imaging and spectroscopy, both put together. And so we're all about light. And you can see the little part of the electromagnetic spectrum where Headwall generally deals is right in here. And so these two black lines are the range that Headwall's instruments cover. And so you can see that that range mostly includes the solar spectrum, which I've shown here in green, and some of those dips in the solar spectrum are the atmospheric absorptions that I like to include, because that's actually the light that we get down at the surface. So most of Headwall's products, or I guess we started as a company mostly concentrating on remote sensing, and so usually in remote sensing, the sun is the source that you use. The price is right, and it's pretty darn bright. And so that's generally the source that we use for our remote sensing applications. And so most of our technology is based around the visible to shortwave infrared region in here. And just to guide the eye, this is the part of that solar spectrum that we consider the visible spectrum. Just right there in the middle, between about 400 and 750, 800, depending on the age of your eyes. So Headwall has a suite of different imaging spectrometers, depending on the spectral range that you're interested in, all the way from the UV to the shortwave infrared. So that sensor right there is a shortwave infrared sensor. It has an MCT detector inside, and if you hear the slight humming of that sensor, that's the Stirling cooler that cools the MCT focal plane array down to 150 Kelvin to reduce the noise of the focal plane that's just inherent in MCT detectors, that you need to cool them down to get nice signal to noise from them. We also have near imaging spectrometers that covers the 900 to 1700 spectral range. An extended V-near sensor that gets you a little bit of the visible and a little bit of the near infrared. and is probably the best sensor if you want to get that region, say between 900 and 1100 or so nanometers, because our other package, so the quantum efficiency of our SWIR sensors is kind of going up at 900. The quantum efficiency of the VNear sensors is kind of going down at 900. And so the best signal to noise in that range is from our extended VNear sensor. And it's also a nice little middle ground. And probably our most popular sensor is the VNear, the visible near infrared, that spans the spectral range from 400 to 1,000 nanometers. So again, just briefly, what is hyperspectral imaging? What is some of the data that you're getting, and what can you use it for? So we like to think of hyperspectral imaging as a way of using spectral fingerprints to identify different objects in your scene. All objects will have a unique spectral signature depending on how they absorb or reflect light. And if that spectral signature is unique within the range that you're exploring, you can identify that object versus other objects that might look similar to the eye, or might just be hard to differentiate from each other. And so the different, I mean, of course, just a small subset of the application space is you can use it to identify minerals, you can use it for vegetation, health, trying to identify disease in agriculture, and also looking at building materials. And so because in hyperspectral imaging, you get the complete spectrum or a continuous spectrum over the whole range where you're looking, you can use things like spectral shape rather than just relative intensity of bands to help identify different objects in your scene. So here is a little graphic of the inner workings of one of our imaging spectrometers. I'll talk about this a little bit more in the coming slides. But our imaging spectrometers are line scanning imaging spectrometers, meaning that they capture one sliver of the scene every time the camera frame is snapped. And so our 4-optic lens will project an image of the scene onto our slit, and then the slit will basically cut off all of the scene except for that little sliver. And if there was no diffraction grating in there, the light from that sliver would bounce off of our optics and just go straight across the focal plane array and get you one little spatial slice of the scene that you're looking at. And because the internal optics are what is called an Offner relay. It's 2 concave and 1 convex mirror. That's just a 1-to-1 imager with very low aberration. And so that's the reason that we chose this design, is that there are no moving parts. There's very low aberration, so there's very low keystone and smile in this design, and the image quality is very nice, and it also lends itself to inserting a diffraction grating. So this is we've turned this convex mirror into a convex diffraction grating to disperse the light in the other dimension that I like to call the spectral dimension. So on your one focal plane array, you have spatial information across this dimension and spectral information across this dimension. So I like to think of it for the airborne package that you saw yesterday as having each sensor has 640 spectrometers in one box. And so each of your 640 spatial pixels is its own spectrometer. And so you can kind of see these lines that I've drawn here. There's a spectrometer, 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 spectrometer. So every time you snap a sliver of the scene, you're getting the whole spectrum at every spatial pixel in that line. So these graphics I like to throw up there to just give everybody an idea, again, of what the image would look like on the focal plane with and without the diffraction grating. So this is just that sliver of the scene, that line scan that we collect with every snap of the camera. And again, if we did not have a diffraction grating, we would just re-image that line onto our focal plane, onto just one little line. However, we do have a diffraction grating, so we spread out all of the frequencies of light from the blue side to the red side for the VNear, from 400 to 1,000 nanometers, for the SWIR from 900 to 2,500 nanometers. So each one of these spatial pixels becomes a whole spectrum across the other dimension. And so then again, with every snap of the camera, we collect 640 spectra or one sliver of the scene. And then to gather a whole scene, we have to either move the sensor or move the scene in order to collect a bunch of slivers to build up a whole 2D image. And that's what's shown on this slide. So in remote sensing, so again, like I said, you have two choices: either move the sample or move the scene. For a laboratory scanning kit, it's easier to keep the sensor stationary and stable and move the sample on that linear stage that you can see in front of you over there. For remote sensing, it's easier to keep the world stationary and move the drone above it. And so that's what we do for remote sensing. And so you can kind of see in this graphic here, this is the direction of motion. And a bit of the terminology that we use with Headwall and a lot of people use in hyperspectral imaging is your ground swath, your swath width, or your field of view is the spread of all your spatial pixels across the ground. The instantaneous field of view, or the ground sampling distance, is the size of one spatial pixel on the ground. And again, as what happens when we collect data is we know the frame rate of the camera, and so every time the drone moves, so we have to match the drone speed to the frame rate. So every time the drone moves one spatial pixel in space, it snaps a new picture, snaps a new picture, snaps a new picture, so we don't miss any ground, and we build up our whole two-dimensional image this way. And then this is just a little graphic of what we call the data cube, which is generally the final data product that you get from hyperspectral imaging. And so this shows a stack of a bunch of focal plane images. So again, every time the camera snaps, we collect the whole focal plane. Then in one dimension is spectral and one dimension is spatial. And then as we're moving along the scene, we're snapping many camera frames and building up this data cube that has, of course, your two spatial dimensions and your one spectral dimension to give you three-dimensional data. So this data cube, the image of this data cube is what we call the band interleaved format. And so it's basically just stacks of your focal plane array put together in a data cube. It's usually, well, it's easier to conceptualize the band sequential format, which is basically just a bunch of 2D images of all of the bands in your scene. And so if you looked at something like this, you could, with your hyperspectral image, show the intensity at 400 nanometers, and then the intensity at 402 nanometers, and the intensity at 404 nanometers, and see all those images in our spectral view software. And again, I'll show you that later today in our live demo. One more thing that I like to cover on this slide, just because it's for people that aren't familiar with remote sensing or imaging in general, it's just a concept that a lot of people just haven't thought of before, and it's something very important. It's one of these you can't get any free lunch things, where there's always an interplay between your field of view and your resolution. And generally in remote sensing, we can adjust the field of view and resolution by changing the altitude at which you fly. So if you fly at a lower altitude, you'll cover a smaller area on the ground, yet you'll have higher resolution. If you fly at a higher altitude, you'll have a wider swath width, yet you will have lower resolution, because the number of pixels on the camera is always the same. So if your spatial pixel is bigger, you're going to cover a wider swath. If your spatial pixel is smaller, you're going to cover a narrower swath. So I guess just to keep in mind when you're planning your missions, there's always that interplay between resolution and field of view. You can cover a large field in one flight if you have a low resolution. You might need multiple flights if you have a high resolution. And then there's of course consequences in the size of your data. If you have really high resolution, you will have of course much more data in the end. I like to have this little graphic illustrates how your lens choice and your altitude go into deciding your field of view. So your lens choice will set what we call your angular field of view, or the angle that the lens kind of, if you picture the lens shooting a laser out of the lens, the spread at which the lens views. And so a longer focal length lens will have this narrower spread or a smaller angular field of view, A wide focal length lens will have this wider spread or a wider field of view. And then as you change the altitude, even though the angular field of view remains constant, the swath width on the ground here, the area that's covered on the ground, will change. And so I just like this little illustration to help people conceptualize, okay, if I get a longer focal length lens, I get this narrower angular field of view, yet I can still adjust my swath width by changing my altitude. And so, again, this is just how we decide what both the resolution and the swath width are when we're planning our remote sensing missions. So now that was the brief introduction to hyperspectral imaging. And so now I'm going to basically give you a little break from the technical talk, and we'll do a live demo. So these were all rocks that were donated to me. I am not a geologist, I'm a spectroscopist. So all the geologists in the audience, this probably means more to you than it does to me. But this is the identification of all of those rocks that are on the sample stage right now. And what I'm going to show to you is gathering of the hyperspectral image and then applying a spectral angle mapping classification to that image to identify the different minerals in the image or the things with different spectral signatures. And so this is what I call the unsupervised classification that I made before coming here, where basically I just said, what are all of the different spectral signatures that I see? What are the different bits that I see in here? And I just assigned a different color to every different spectral signature that I saw. And here you can see the spectral shapes of all of those different spectral signatures. And so don't worry, I can put this up later. But for now, I'm going to switch your view to the view of my computer over here for the live demo. And we'll just briefly go over the workflow for a laboratory scanning situation. I've connected via remote desktop to this control computer. And I've pulled up Hyperspec 3, which is our control software. Oh, I better use this so they're not going to hear me. So I've pulled up Hyperspec 3, which is our control software for our imaging spectrometer. So now the general workflow that I go through, part of this I've already taken care of. First things first, I like to leave the lamp on for about 15 or 20 minutes just to have it heat up and give me a nice stable output. So the lamp's already been on for a bit. And now in spectral view, you can see that there are a series of buttons here that give you control of different parts of the instrument here. So the live view will show the whole focal plane array that the imaging spectrometer is looking at right now. I've connected via remote desktop to this control computer. And I've pulled up Hyperspec 3, which is our control software. Oh, I better use this so they're not going to hear me. So I've pulled up Hyperspec 3, which is our control software for our imaging spectrometer. So now the general workflow that I go through, part of this I've already taken care of. First things first, I like to leave the lamp on for about 15 or 20 minutes just to have it heat up and give me a nice stable output. So the lamp's already been on for a bit. And now in spectral view, you can see that there are a series of buttons here that give you control of different parts of the instrument here. So the live view will show the whole focal plane array that the imaging spectrometer is looking at right now. Yeah, so nobody saw my buttons. The live view over here shows what the imaging spectrometer is looking at right now. So right now I'm kind of pointed at a hole between my little sample stage right here. And so if I use the motion tab and I move on top of my white reference, you'll see a fairly uniform response across my whole focal plane array. You can see that it's dipping a little bit at the edges because there is some Gaussian profile to our lamp source. So we're a little bit dimmer at the edges than we are at the middle. This is a quartz tungsten halogen lamp, which gives nice broad illumination all the way from 400 to 2500 nanometers and a little bit further on either side. However, we generally only care about 400 to 2500 nanometers. And the spectrum, well, and you can also see on here, where's my crosshair? You can click on basically any part of the focal plane array, and you can see subsets of it over here. So now here you can see the spectrum of this spectral pixel right here, and now you can see the spatial stripe across here as well. Yeah, this is just the live view of the imaging spectrometer, and you use this view to also change the exposure time and the frame period. So now, the next bit of the normal workflow would be to set your exposure time to something that is reasonable. And this window right here, this calibration window, shows a histogram of all of the pixels in your focal plane array. And so this is a 16-bit camera, so it saturates at 65,536 counts. So I want to have my maximum counts a bit below that, so I'm not saturating my pixels anywhere. And some of the darker spectral bands are going to have lower counts that you can see down here. And so this is basically just a histogram of all of the pixels in there. So if I increase my exposure time by a lot, you can see that both on this screen and in the histogram that I'm saturating a bunch of pixels. That's not good. If I lower my exposure by a lot, you can, of course, see that I'm not optimally illuminating my sample. And I always like to check this through this calibration window to see the histogram of the whole focal plane. A lot of people like to just look at this little window right here and do it more visually. I guess I'm more of a numbers guy than a visual guy. And so when you are happy with your the illumination on your focal plane array, you can click Collect White Reference, and we will always provide a little piece of Spectralon, which has a very uniform reflectance across your whole spectral range. And we use this to approximate what is about 100% reflectance across everything. And so when I click Collect White Reference, this will basically gather what we call a full frame white reference. So a calibration of all, in this case, 384 spectrometers in there. And after that, you would click dark reference, and that just takes care of the dark noise of the sensor. That should also be done definitely every time you change the exposure of the frame period, but otherwise anytime the sensor's been sitting for a while and maybe changing its temperature, internal temperature in there, can affect the dark current. So yes, you can apply a profile to the gathered spectrum that you have, which we do with our TARP. You can apply that same single, so I guess not for the full frame white reference, that's not currently in there, but for if you use a scene white reference, you can, so basically if you use one spectrum, you can apply that across the whole way, so that the same way that you would. I would assume that this Spectralon is calibrated because we get Spectralon and we get I guess Spectra with each delivery of the Spectralon. It's just not built into the software to automatically apply that, I guess, calibration standard. The other buttons on here are the capture window. And so this capture window you can use to basically set up the capture of the data on the stage here. So the first line is for the prefix. So every time you save a data cube in the software, it will be appended with the timestamp that the data was collected. And so this allows you to name it something else along with the timestamp. So the prefix just means this is what's going to come before the timestamp. So if you don't change the name, you'll never overwrite the data. You'll always just have a new timestamp. But this will allow you to keep track of which sample is being collected. Here you can see the device speed and the start and stop of your image. And the easy way to set the device speed is to put our calibration standard in front of it, which is just a bunch of 1 centimeter spaced lines. And since the sensor knows that these lines are all spaced by 1 centimeter, it can use that information to calculate exactly how far the sensor is from the sample, and so figure out its spatial pixel size. And it also knows what the frame period is, and so it will calculate what the speed of the sensor is just by hitting this calculator button. And you can see that the speed of the sensor for square pixels is 10.9 millimeters per second. And I've already set the start and stop positions of this capture. And finally, the last window is the waterfall window, which is actually a very helpful window to have because, again, you're only gathering one sliver of the scene at a time. And so in order to kind of visually see what's under your stage in a normal looking image, you need something with a little bit of history as you've passed by the image. And so this waterfall gives you a little bit of history of the image as it's come out. So if I just move the stage to the end, oops. You can see the image appearing on the waterfall. And again, this is just telling you what's already passed by the imaging spectrometer. And so you can see all of the rocks coming out here. And so that was just an example to show the operation of the waterfall. And I often use the waterfall to help set the bounds of my images or to make sure that I'm getting the field of view that I want. And you can, of course, adjust the field of view by sliding the sensor up and down this rail to change the swath width and resolution of your scanning kit. And so now I'm just going to press go. And you can see that it's moving back faster than what it should for square pixels. And so you have kind of a condensed image on your waterfall here, which is a telltale sign that you're moving at the wrong speed. And now we're moving again, of course, at the right speed and gathering a full data cube of these rocks on the scanning kit. And so now I'm just going to move the sensor back to the spectralon because this light actually produces quite a bit of heat, so I want to leave it sitting on something that reflects most of the light off of it so I don't gather heat on the table and everything. And so now this is just what I would call a quasi-RGB image of these rocks because I only gathered shortwave infrared light. There's not going to be red, green, and blue bands per se. But yeah, so this is just a way to visualize this data cube. And now the next step would be to open up that data cube in our analysis program SpectralView. So you just have to navigate. And so this is the one that we just took. And so the data file will be the one where the full frame white reference was applied, and the raw file is going to be just your raw digital counts. And then you have your full frame white and dark references also saved in here. So if I just double click on the header file, I can open up my data cube that I just took in SpectralView and zoom in a little bit here. So now you can see the image up there, and in SpectralView, there's this little spectrum icon that if you pull up, you can see every spectrum, or wherever my cursor is the spectrum of that spatial pixel. So if I just click on a few of these different spectral features, I can see some of the different spectral features that show up on these different rocks. And now I'm going to quickly open up the classification module to show how our classification software works. So I'm going to open up an image, the image that I just took today. And so now you can see up here our classification model or module. And now this module uses spectral angle mapping to help give a false color image of all of the different spectral features in your scene. And so to add a new spectral reference, I click Add Reference here, and SB1-1, and I'm just going to click on this spectral feature. If I click on this, I can change the color that I want that spectral feature to be. And if I click Update Spectra, it uses spectral angle mapping with kind of a preset threshold, and it finds all of the spatial pixels in my whole image that pass that threshold, and it averages them all into this red spectrum up here. Well, I know that I don't want to include pixels from this other rock, so I can trim down the spatial region that I use. And so if I hit recalculate here, now the red pixels are the pixels that have passed my spectral angle mapping threshold, but have not passed my spatial exclusion criteria. And the green pixels are all of the ones that are being included in this average right now. And you can also see the difference between the seed pixel, or that one pixel that I clicked on here, and the average of these 3,396 pixels there. And then down here, I can also change the threshold and press recalculate if I want to have a little bit of a tighter threshold on all of the spatial pixels that I'm including in this average. And generally, I use a tighter threshold when I'm creating my reference, and then I'll loosen up the threshold when I'm actually applying the model to the image. And so now if I click Classify, it will compare the one reference in my library to every pixel in the scene, and every pixel that matches this confidence interval will be colored. What color did I make it? Orange. And so now you can see all of the orange pixels here. I'll click on, I'll just make a few other references. I'm not going to do a complete classification here because that would probably take more time than everybody wants to sit and watch right now. But now I can see that most of the spectral pixels are on this part of the rock, but I'm just going to include this region here. And I think that's probably pretty good for my average spectral signature. So I'm going to update that, and I'm actually going to increase the threshold a bit. And now if I classify, I'm getting mostly all of this rock here. And also, like I showed in the other screen, we have a spectral window here as well that you can, again, as you mouse over the different regions, you can see what all of the different spectral signatures look like. And you can also, in the spectral window, display the reference spectra that you have just taken. And these spectral features can also be exported to be used in whatever other software you'd like to process spectra in by just clicking Save Graph. And then this will save a CSV file that has all your spectral bands and all of the intensities for each of the spectral features in there. And now I'm actually just going to pull up a model that I made of these same rocks a little while ago that includes more of the spectral features. And so this is more of a complete demo, and this is actually from the same rock, but it's a different side of it, I guess, than last time. So you can see that I'm missing some of these spectral features because this mineralogy was not on the other side of the rock that I actually previously classified. But here you have most of the spectral features classified. And I guess if I go back to my talk, you can see what all of these spectral features look like, and I guess what it would look like if I was on the other side of the rock. And so I guess I think I've given a little better names to them over here. But I mean, here you can see all of the different spectral features of the, I guess, the different mineralogy in these rocks. And again, if anybody else has other rocks that they're interested in scanning, I'm happy to do that later today as well. And so I guess, again, before I move on from the demo portion of this, I just want to ask if anybody has any questions on the demo portion, keeping in mind that you'll absolutely have an opportunity to use this yourselves later in the day. So that sensor is 640 wide and 268 spectral pixels. This sensor is 384 spatial pixels wide, and it's escaping me how many spectral pixels. I think it's about 170, but I'd have to double check our data sheets over there. Oh, it depends on how far you scan. I guess in this example, let me go back. Oh, actually, and and I guess right here, I guess my 170 was pretty close. There's 169 spectral bands on this WIR 384. Yeah, so all of our, I guess if I didn't mention it before, all of our data is collected in the standard ENVI format, so it can easily be imported into ENVI. Well, currently we just output ENVI formatted data. I mean, honestly, at the end of the day, it's a binary data cube that if you read the header with whatever program you might write, you can read it. I've written Python readers. I've written readers. I guess we have readers for MATLAB. But right now, all of the data is stored in the ENVI format. So the height of the altitude above ground level of our flights yesterday, depending on the flight, most of them were around 50 meters above ground level. So I actually have a little calculator that I can pull up for that. My offhand guess is that they were about 4.5 centimeters per pixel. Less than that. But here's just a little Excel calculator that I have, and yeah, and I guess if we went to some of our lower flights were done at 20 or 30 meters, and so that would have been 1.2 centimeters or 12 millimeters per pixel. And if you fly at the ceiling that a drone can fly at without getting special permission from the FAA, 120 meters, you're going to get 7.2 centimeters per pixel on the SWIR. And it's almost exactly the same on the VNIR. So some people have put our sensors on satellites, and we are working with other agencies to put more sensors on satellites, but I can't really comment more on that due to NDAs and stuff. So there's at least one up there now. Yeah, so moving on from the live demo, this is just showing some of the different packages that you can use to deploy these hyperspectral images, or these hyperspectral imaging spectrometers. So the package that you saw yesterday is our co-aligned VNIR SWIR, and actually the one you saw yesterday is the co-aligned VNIR SWIR with a LiDAR attached to it, and so you can see the Velodyne Puck Light LiDAR attached to it over there. We also have the Nano Hyperspec, which is our VNIR sensor, which is one of the sensors that is inside that co-aligned. And that sensor is actually small enough to also fit on a gimbal. And we also can deploy the SWIR sensors by themselves on a drone as well. And for ground-based remote sensing activities, we can supply our sensors on a rotation stage as well. So you could say image a hillside or something like that from the ground. So now I'm just going to briefly talk about the data that we get from our sensors and the kind of a quick overview of the workflow for the remote sensing data. So when our sensors are gathering data, we are recording the digital numbers from the sensor. So these are just the straight numbers that are read off of the sensor, and we record them as 16-bit unsigned integers. So these digital numbers will, of course, contain the chemical information that everybody's interested in, but they'll also contain atmospheric absorptions. They'll contain detector characteristics and characteristics of the light source and characteristics of basically the system optical performance and things. So if the whole optical path, including the lens and things like that, could have will always have some effect on the shape of the spectra as you're gathering them. So all of our remote sensing imaging spectrometers are radiometrically calibrated at Headwall, and that radiometric calibration will give you an absolute measure of the amount of light that is reaching the detector in spectral radiance, and this will eliminate all of the features of your system optical properties and your detector characteristics. So you'll kind of eliminate any non-uniformities in your focal plane array or your whole system optical setup. But you will still get, since it is just the amount of light reaching the sensor, it will still follow the shape of your light source. And as you can see here, in this radiant spectrum of the sphere, there's some of the atmospheric absorptions are out, and the general shape of this spectrum looks a lot like the sunlight that's getting to your sensor. So you also want to be able to correct for the sunlight and essentially go to reflectance, which at its core is a measure of the amount of light getting to the sensor versus the amount, or divided by the amount of light hitting your sample. And so ultimately that's what you want. Because the amount of reflectance only depends on the absorption and reflectance characteristics of your sample. And so we use our reflectance calibration tarps to convert to reflectance in the field, which you saw us flying over that 3 meter by 3 meter tarp yesterday. That has 3 panels that we know the exact reflectance of, and so we can apply that known reflectance to the measured reflectance to finally get out reflectance. And so you can see here that some of, well, these atmospheric absorptions right here, you still shouldn't include in your analysis, but they don't look like they're down to 0 because you're basically dividing by 0 when you are converting to reflectance. And so now I'm just going to briefly talk about what one would normally do when analyzing this hyperspectral data, and kind of the general workflow for hyperspectral data analysis is often you want to create a ground truth spectral library to compare your remote sensing data to. So you can do that a number of ways. You can use something like an ASD field spec, or you can use our imaging spectrometer and basically either in the lab or out in the field take images of things that you know what they are, and then when you get the known spectrum of that, you can apply it to your remote sensing data over a much larger area and say, where is this spectral feature in my remote sensing imaging? And at this point, I'm just going to show some example data that we took on our rotation stage at Saginaw Hill in Arizona. Which the reason we chose this is because some of the researchers that we were partnering with characterized the mineralogy of this hill fairly well, and so we wanted to take some hyperspectral images of that and see how our spectral images compared to what they expected the mineralogy to be. We don't have a standard way to import those libraries into our classification module currently, but I guess I have hacked a conversion of those libraries into our JSON format. So, I mean, it is, of course, possible. It's just a matter of converting the spectra to the right format. Data is data, but yeah, you just have to put it in our format. It could be used, but yeah, as part of our package, we don't have currently an importer. So in all of these images, I'll basically be showing you two images. One, which is just a camera phone image of what we are capturing in the scene, and another one is going to be what we call our quasi-RGB image. So where the red band is 1597 nanometers, the green band is 1203 nanometers, and the blue band is 1040 nanometers. And right here, you can see again, what I like to call my unsupervised classification. So this is where I just took the data and kind of blindly said, what are all of the different spectral features in this scene? And so I, one by one, assigned all of the different spectral features, and then at the end created a false color image that was all of the different spectral features that I found over here. And I did that also for an outcropping, where again, here's our camera phone image of the outcropping, and here's the SWIR RGB image. And again, you can see the unsupervised classification. So basically just a map of all of the different spectral features, or hopefully different minerals in this outcropping. And then this last set is mostly a pile of rocks that was near to the researchers there. And the kind of neat part about this is one of the geologists there had some sort of copper ore in his pocket. And he said, I'm going to throw this copper ore into this pile of rocks, and you image it, and you better be able to find my copper rock because it's different than all those other rocks there. And so that was just sort of an on-the-spot test of, can we find a unique rock in a pile of I guess, more normal rocks? And yes, we can. The spectral shape of that copper rock kind of stuck out like a sore thumb, so it was fairly easy to characterize. And then we partnered with our friends at the University of Arizona that looked at all of our spectra and then gave an assignment to all of the different spectral features that we saw. So most of these different spectral features here were different combinations of muscite, illite, and sericite, and the reason they showed up as different spectral features is there were different amounts of sericitic alteration in the minerals there, and that's what we were picking up as different features. I don't really know what that means, but they just told me to say that. So also on the outcrop, the yellow stuff was either illite or smectite, and they said that they couldn't definitively tell which one was which because the peak at 1900 nanometers is covered up by the atmospheric absorption, so they weren't positive. And they said this copper rock was a mix of chrysocolla and malachite, and I apologize if I'm butchering the pronunciation of those minerals. This example I like to show because it is another example of some airborne data, and this is over a mining leach pad. And unfortunately, we don't have the work of the scientists on this yet. We only have my naive classification of this, or my unsupervised classification. But this is, again, just to show a false color image and all of the different mineralogy that we're seeing in this leach pad here. And this is all of the spectral features with the coloring being the same as what you see here. So I guess I'm happy after the talk to let anybody that is interested in looking at these spectral features or that can tell more about these spectra look closely at this if they would like. But for now, I'm also going to briefly talk about our LiDAR packages, because this is one of the things that sets Headwall apart from some of the other hyperspectral imaging companies in that we provide an integrated solution with both LiDAR and hyperspectral imaging all on one package. We've taken care of all of the integration and give you an operational drone with both LiDAR and hyperspectral imaging on it. And so LiDAR is, of course, light detection and ranging. It's akin to radar, and instead of using radio waves, you're using shorter wavelength lasers, so you can get a bit better resolution than radar can. So these are some views of the data being captured by the LiDAR. So this dimension is the spread of that LiDAR as it's going out. So if you look at the Velodyne LiDAR over there, the kind of dark greenish bluish looking window is the window where the laser comes out, and there are 16 pairs of lasers and detectors that are spinning around there and basically gathering returns as they go. And so each of these lines are the returns from one of the 16 lasers as they're going past, and this is our direction of flight. And so as we fly, you'll fill in these gaps between these between the 16 lines, and you'll build up a much more dense point cloud that will basically give you a 3D rendering of everything in your scene, which in the end looks really cool. And so this is just, well, these are some images of our LiDAR tools software package. And so our LiDAR tools package has a couple of different tabs. And the first tab is just one that can create the last file. And so that stands for laser, and don't ask me why the LiDAR people decided on that, but that's the standard type of LiDAR point cloud file. And so basically, when LiDAR is running, it's just getting a bunch of return data and also a bunch of GPS IMU data, and we are putting those together to actually say where these different points in the point cloud are in space, and creating a file format that you can read using free rendering software. We usually recommend Cloud Compare. Another tab that we have here is called the Create DEM, or Create Digital Elevation Model tab, where you can take the LiDAR data and use it to create an almost arbitrarily spaced DEM of whatever you've flown over. And this has the big advantage of allowing you to have real-time kind of terrain measuring, so you really know the shape of all of the terrain that you have flown under, and that greatly helps in the orthorectification of the hyperspectral imagery later. And the final tab is the fuse hyperspectral imaging to the DEM. And so we can take the DEMs that we've created and add them onto our point cloud and basically make it an extra spectral band in your point cloud is your DEM, to basically allow you to visualize the DEM along with your point cloud at the same time. So this is just some LiDAR images, actually some DEMs taken over a steep hillside in Utah. And this is where you can really see the advantage of using a LiDAR DEM to do the orthorectification. Again, this is the point cloud that we started with, and this is the DEM that was created with 10 centimeter resolution out of the LiDAR point cloud. And this is the hyperspectral data using the USGS DEM to correct the image. And so basically, you can see here that we were doing a pretty good job of terrain following. However, the USGS DEM thought that the distance between the camera and the ground was changing a lot as we were going by. But the LiDAR DEM knew that we were following the terrain, and basically the fact that we knew the shape of the Earth much better with much higher resolution with our LiDAR DEM allowed us to correct the imagery much better over this steep hillside. And this is just a final image of the Fuse LiDAR tab, where it's a pretty simple window where you just select the type of DEM that you want to fuse and press go, and it will output your fused data cube. And so now this is just some examples of our fused LiDAR data just taken outside of Headwall. And this is also where, so we are at our heart a hyperspectral imaging company, yet we're moving into the area of LiDAR, and people asked us to fuse the data, and so we did that. And this is just one example of using one of these fused DEMs to visualize your data. And I always like to ask the audience what they would use LiDAR for and what applications they would use, so we can think about how we will develop it going forward. But this DEM right here is the standard deviation DEM, which shows very big changes whenever there are large changes in elevation. And so this can be used to, I guess, very easily see all the trees in the scene, because a tree will be high at its top, and yet you'll also get ground pixels in there as well in the LiDAR point cloud. This is another view of that same scene that we took, again with one of our LiDAR DEMs that was fused to the data, and just basically an example of what this data looks like. And here we have the standard deviation DEM. Here we have the max DEM shown here. And here we just have an RGB image of all of the same data set, just as a display of the fusion capabilities of our LiDAR. And with that, I'd like to thank everybody for their attention and say, so we started off with a brief introduction to hyperspectral imaging. We saw some examples of how the starter kit operates, and then we talked about a few of the many applications of hyperspectral imaging. And I very much encourage any of your questions or and invite anybody that wants to come and play with our instrument. So thank you very much for your attention. Does anybody have any questions? Oh, so the question was about reflections from the propeller in the LiDAR imagery. And yes, because the LiDAR is spinning around in 360 degrees, you'll get returns from all directions. And we often use the propellers as kind of or the point cloud from the propellers as a map of our flight path. Because if you look at the propellers, you can see in the LiDAR point cloud exactly where you flew. But in general, before we display the data, and part of the analysis process is we crop that stuff, because usually people don't want to look at the returns from the propellers. They just want to look at the scene under them. But yeah, so in all of that data there, that basically any returns that we got above the aircraft, we truncated, because you can get some glare from the sun coming into those detectors. You can get other random things, and we just throw all that away. Yeah, so I think you're getting at, I guess, what we like to call point level fusion versus pixel level fusion. And we thought about doing it both ways. And basically, we ended on doing what we call the pixel level fusion, or the fusion of two of the DEM to the hyperspectral data, mostly because of data size concerns. So basically what he is talking about in what we would call pixel level fusion, every point in the LiDAR point cloud could be assigned a spectrum from your hyperspectral image. You will have many times more points in your point cloud than you will hyperspectral spectra, and so you'd end up with a bunch of redundant data. And I mean, we're still considering ways to have a pointer or something to a group of pixels and say this whole group is going to be from this one spectrum, and et cetera, et cetera. But I mean, this is part of why we're reaching out to people to see if there is a huge demand for something like point level fusion of the LiDAR point cloud. But so far, we've only done pixel level fusion, basically using the resolution of the hyperspectral imager as kind of the limiting factor in the fusion that we're recording. We have not done any ground LiDAR with vehicles. All of our LiDAR packages are designed to be airborne. So I guess the question is, I guess so we have not used other people's LiDAR measurements for our DEMs and things like that. Is that what you're, I mean, you, okay. Yeah, yeah, absolutely. Charlie has that on his computer, so we can, yeah, we actually have a pretty cool looking LiDAR point cloud of a bunch of the buildings over WashU. And so the maximum data rate you can get, gosh, I knew these numbers off the top of my head. I believe it's something like, um, I'm not going to try to speculate on that, but I can get the numbers for you when I look at my computer later. But in general hand waving terms, um, the data size of like the stuff that we gathered yesterday, I think we did 4 flights, and that was a total of about 120 gigabytes of data on the flights that we did yesterday, and so about 60 gigabytes per sensor. And so uh, in the raw form before it's been processed and converted. We do have dual returns, so you will get stuff below the trees. However, of course, there will always be less returns under the tree because some of the returns are from the top of the tree. But yeah, you can, as I zoom in on the trees a little bit here, you can see that there are still points on the ground under the tree. It does not do any automatic classification or anything like that. It just produces the point cloud using both returns usually. However, I mean you could turn one or the other off. Uh, well, after we produce the last file, it will just be a point cloud like this. Um, so we are not filling like that spectrum part of the return. Yeah, I'm not positive if every point has metadata as to whether it is from the first return or the last return at the end. I'll have to double check with our software guys on that question, but I'll definitely get back to you on that. So 2.7 gigabytes is the size of the LiDAR point cloud. So we support, I guess, 4 different types, where one is the max within whatever resolution you've decided. So basically, if you make a 10 centimeter resolution DEM, the max would just be the highest return within that 10 centimeters. The min would, of course, be the lowest. We also have the mean and the standard deviation are the 4 types that we support now. Oh, I guess I have not gotten rid of the buildings before. You mean? Oh, no. Like we're using the buildings in the DEM because the LiDAR or the hyperspectral data will be getting reflections from the top of the building. So we want to include everything in the scene in the DEM. We don't have a formal API for any of those. I guess for MATLAB we have a loader that I can send anybody that wants it to load the files in, but otherwise we don't have any other analysis tools. And yeah, again, Python, it's mostly just my personal stuff. And again, I generally don't have a problem sharing my personal stuff if you ask me specifically. But yeah, I think now is time to move on to